electrical stimulation of the human body has been going on for a long time. In our studies, what we try to do is generate a big magnetic field over cortex, and we want to induce either excitation of the cortex or we want to induce inhibition of the cortex. The physiological effects of TMS are actually not very well understood. We kind of know that they have effects at the level of a single neuron, at the level of a synapse, and even at the level of network. And we also know from imaging studies and other types of technologies that you don't just influence cortex in one region of the brain, but you also influence cortex that's linked to that region in other areas of the brain. So it's very likely that when you apply TMS, you're not just having a local effect beneath the coil, but you're having an effect on a whole neural system, and you're regulating its activity. The clinical applications of TMS far outpace our physiological explanations of their effects. So we have a much better notion of what TMS can be used for than how it actually works. So in psychiatry, you can see that there are a number of conditions for which TMS has been used, including depression, mania, obsession, schizophrenia, catatonia, PTSD, and even drug cravings. In the neurological sciences, Parkinson's disease, dystonia, tics, stuttering, spasticity, epilepsy, pain, and the topic I'm going to talk about, tinnitus. What is tinnitus? Tinnitus is perception of sound in the absence of external stimulation, and it's typically been linked to cortical excitability. I heard an NPR show one time where they were talking about tinnitus, and they had a nice sound effect. They played high buzzing sound as the person was talking about tinnitus, and it was really annoying. You're trying to listen to this announcer, and you basically can't hear him because there's this loud sound. And that's what patients with tinnitus go through. So they're constantly bombarded by an internally generated sound that can be very, very loud and annoying. We've had patients who talk about the sound being like planes landing, and they hear it all the time, and it may be louder at night when they're trying to go to sleep. We have patients talk about their tinnitus sounding like millions of crickets at a very loud level, and that being constant throughout the day. I recently went to visit my parents and took my family up to St. Louis, and we went to the Anheuser-Busch bottling facility. And during the tour, you go through the bottling room, and there are thousands of bottles of beer running down these little steel rollers, and it creates a really high-pitched, very loud sound. Everybody in there's got ear protection on, but none of the visitors have any ear protection. We're just going through. So it's really annoying and loud. And I told my spouse that a lot of patients with tinnitus tell me it's just like this, and she's like, "Oh no, really?" So it's a very distressing condition, and the comorbidities of tinnitus include anxiety and depression, and a significant number of patients with tinnitus don't receive any benefit from those medications, and we frequently hear of patients who have committed suicide because of their tinnitus. So it's very agonizing, and that's why people come forward when there's new treatments. A lot of people report the same thing, where they'll be engaged in some activity where there's loud noises, and that seems to have an effect of damaging hair cells in the inner ear, and then that promotes or leads to this condition of tinnitus. So I think there are several components to tinnitus that reflect the whole neural system that promotes your awareness of this sound. Like all sensory stimulation, we can habituate to it, right? So if you walk into a room and there's a foul odor, after a while you won't detect the odor too much because you've habituated. But if there's a dead carcass in the room, you're really never going to habituate to that, right? And you're just going to have to get out of there because it's so distressing and annoying. So somehow tinnitus takes on that kind of characteristic where it's something that you don't habituate to, and it's probably because it's not an external signal. So it's much more difficult to habituate to something that's internally generated that way. People have shown that you can image these areas that are thought to be overactive in the cortex, and this PET scan was published in one of our studies, and it basically shows an area of increased activity on PET in one temporal lobe relative to the other. PET is an imaging technique. It's called positron emission tomography, and PET basically looks at oxygen utilization in the blood, and that's an indicator of how active neurons are in regions of cortex. And so the idea of our study was that we could take TMS at a low frequency, which should suppress neuronal activity. We could apply it over that area where there's excessive neuronal activity and hopefully correct the tinnitus perception. And this is kind of the image-guided technique that we have. We first get these PET scans that I showed you before. We try to identify areas of cortex that are overactive. Where the magnetic field is the strongest, we can put it over top of this area that was designated on the PET scan and deliver TMS. And so this slide shows Dr. Dornhofer, myself, and Casey Shillette, all of us who have tinnitus. Tinnitus tends to improve in about half of the patients who we treat. And we don't have a good understanding of who's going to respond and who's not. And many studies have kind of looked at that. There seems to be some indication that maybe if you're younger, maybe if your tinnitus is not as severe, you might have a better response. But in fact, we're treating people who are 75, who have tinnitus for 30 years, and they respond. So the bottom line is we just don't know who's going to be a responder and who's not until they actually get treatment. And of the treatment responders, the typical response that they get is a decrease in the loudness. And probably just as importantly, they tell you that they're not aware of their tinnitus, whereas before it dominated their consciousness. So this was actually a really exciting part of doing research. I mean, for years I was engaged in research with neglect patients, and I can tell you that it was never as satisfying as having somebody come in after we had treated them for tinnitus and then telling us, you know, I don't have tinnitus anymore. I just don't have it. I've had it for 10 years and I don't have it anymore. This is fantastic. I mean, people would come in and say that. So the lab would get, understandably, very excited because there is no cure for tinnitus. So we really felt like we were doing, you know, people a lot of good. After a couple of weeks, people would report to us that their tinnitus started to come back. We find that 20 to 50% of responders get longer lasting relief from maintenance therapy with TMS. And this is something we kind of developed uniquely here at UAMS, and it just seemed like an obvious thing to do, but no one had done it. If someone's tinnitus went away for a while after TMS, you simply reapply it when it comes back. And what we want to do is see if we can lengthen the amount of time that they go with longer relief. So that was novel. We did it in one patient and published it, and we've got a series of patients going through maintenance now. And it actually seems that a subset of the patients who responded to tinnitus do a lot better with maintenance therapy. And we think this is a good concept, that TMS can be used not just like a one-time intervention, like a surgery, and that's the way it's typically been applied, but you can actually use it more as a therapy, so you're trying to condition cortical tissue over time. There's a lot left to understand about the effect of TMS on the brain and how it can be blended with imaging studies to get at mechanisms. But we're very encouraged by the fact that we can perhaps treat up to 25% of patients who have tinnitus, which translates to millions and millions of people in the U.S.